In addition to the outline I gave you the other day, last Friday, when I still had my school keys, I gave you an outline to study, but now I want to give you, kind of refine this a little bit. And you can use this as your equation list. And the first part of the final is going to be on momentum, conservation of momentum, and so on. And so here are the equations you need for momentum, right here. There's only 3 equations. Yeah?
Is the test all multiple choice?
Yes. Now, the test is all multiple choice. So, momentum equals mass times velocity. That's the definition of momentum. And then over here, I decided to give it a variable name. This is the impulse momentum theorem, where it says impulse is the force applied to an object multiplied times the time that force is applied. And that impulse will result in a change in momentum of the object. So now this is in the review outline, so do that. This is the impulse momentum theorem. Make sure you study that. Now, in another situation, you'll have situations like collisions or explosions where momentum will be conserved during that. Now, that's the key idea, is to know when you read a problem or read a question, you have to ask yourself, what situation am I looking at? When you're looking at this situation where momentum is conserved, you need to know that that means that there are no net outside forces acting on your system. That if 2 objects collide, they apply equal and opposite forces. Those are internal to the system. There are no net external forces acting, and thus momentum is conserved. So study the conditions under which momentum is conserved. And then you'll know which equation to use depending on what the problem is. Now what I have over here is a quantity chart, and I've made these for you before, but I don't think I've put them all together for a whole semester like this. So here's the quantity momentum, the variable lowercase p with a vector hat on it, and it has units of kilograms meters per second. Not sure why they don't have a special name for this collection of fundamental units. They don't. You just kilogram meters per second. And we have mass and velocity, which we're familiar with. And then I went ahead and include impulse and time, because they're in these equations here. So this is a nice thing to do when you're making an equation list, to keep a quantity chart. And then you also have the units here. So you'll know what unit of measurement we use for that quantity. Then we have the next unit is work and energy. And that's all of these right here. These are the equations that you need for Unit 8, I believe. And of course, this is the work-energy theorem. So you'll need to know the work-energy theorem. This is the work done by the net force will be equal to the change in kinetic energy. Are you hearing that?
Yeah, there's 2 birds out there.
That's nice. Okay. They're just trying to get together out there, you know. That's what we all want, really. All right, now, then here we have kinetic energy. Kinetic energy is the energy that an object has because it has mass and it's moving. You throw a baseball. That baseball has energy contained in its mass and its motion. And we call that kinetic energy. It took work to get an object to give an object kinetic energy. Here we have gravitational potential energy, MGH. And this is the work that gravity can do. If you release, like if you're holding an object above a certain height, if you release that object, gravity is going to pull it down. The object will move down, and gravity will do work. Of course, when gravity does work, and if gravity is the only force doing work, all that gravitational potential energy will turn into kinetic energy as it accelerates downwards. Then we have the definition for work here, the equation for work. Figure out your force times your displacement, and then look at the force and the displacement and check the angle between them. There is a problem on the final that I've already written where there is an angle between them. So it's the force times the displacement times the cosine of the angle between them, and that will give you how much work is done. And work is when you exchange energy from one system into another system. And when Connor throws a baseball, he's delivering energy from his arm, transferring it to the ball using a force. Applies a force to the ball. You do work. The ball now has kinetic energy. But of course, you can apply a force and give an object other kinds of energy, like gravitational potential or elastic or whatever. But in any case, work is when you transfer energy using a force. Then we have the definition for what we call mechanical energy. E is the variable we use. By definition, it's equal to the kinetic energy plus any kind of potential energy we have. We only use really gravitational. I don't think I'm not going to give you an elastic potential energy problem on the final. And of course, this is if gravity is the only force doing work in your system, then the total mechanical energy, since it's the sum of these two, is not going to change. The total mechanical energy will remain constant. That's conservation of mechanical energy. So the initial mechanical energy will be equal to the final mechanical energy. And there'll be a problem where you start here. And then over here, of course, are all the variables, all the quantities, their variables, and their units. Now, I do want to emphasize, make sure that, again, when you are look at the problem first and then ask yourself what concepts that we've learned apply to this problem. These are just shortcut ways of expressing those concepts. So if you understand the concept, that will tell you which equation to use. Okay? Oh, very good. Okay, thank you. All right. The next unit we studied was, Unit 9 was on thermodynamics. And these are the equations you need. Remember, this is not complete. You still need to study. Read the book, read your notes, work some problems that we've already worked, and so on. You need to understand the idea of heat. What is heating? And heating is when thermal energy is being transferred from one thing into another. Of course, heat only flows from a high to a low temperature. What do we call it when things are at the same temperature and heat is no longer flowing between them? There we have a name for that. It's called thermal equilibrium. Yeah, that's a question on the final, by the way. Thermal equilibrium. When things are at the same temperature, heat won't flow between them anymore. But if there is a temperature difference, thermal energy will flow. And that's what Q represents. Now, we represent that flow of energy with with joules. I mean, that's the unit we're going to use, and here's joules. Of course, chemists and dietitians and so on can use calories or kilocalories and stuff like that. But in physics, we tend to use joules for measuring heat. Sometimes when you add heat to a substance, you will make it hotter. You will raise its temperature. And, I didn't put that on here. I didn't put T on here. I'll put T. Temperature. And temperature is measured in degrees Celsius or kelvins. I'm not going to give you any problems with Fahrenheit on it. One thing to remember is that if you have a change in temperature, the delta T is the same whether it's in kelvins or degrees Celsius. I mean, if you say I increase the temperature by 40 degrees Celsius, that means you also increase the temperature by 40 kelvins. For some reason, we don't say degrees Kelvin, but who cares? Right. So here's heat, and now this is the mass. This is how much stuff we're going to change the temperature for. This right here, specific heat capacity. That's a property of the material. Some material, you need a lot of heat to change its temperature for a given mass. That is a high specific heat capacity. Like water. Water has a really high specific heat capacity. Other materials, not so much, like aluminum. Doesn't take a whole lot of heat to raise the temperature of aluminum. It all depends on the stuff. Sometimes when you add heat, you change the state of the object. And that's what the heat of vaporization and heat of fusion are all about. And we talked about this yesterday. But the units for heat of vaporization and heat of fusion are joules per kilogram. Look at specific heat capacity. Joules per kilogram degrees Celsius. So how much stuff you have and what is the temperature change matters. Here, temperature doesn't affect these. It's just how much stuff do you have? How much energy do I need to melt a kilogram of this substance? Yes?
So with a specific heat capacity, is it multiplying by degrees Celsius, okay, or divided?
It's, the question was, do we multiply by degrees Celsius or divide by it? You divide by it. I mean, look at the equation here. If I were going to solve for C, solve for the specific heat, this is measured in joules, divided by kilograms, divided by degrees Celsius or Kelvin. Does that make sense? Okay. Yes?
You either divide by the kilograms or degrees Celsius?
You're dividing by both. Okay. Now, this right here, Q1 plus Q2 equals 0, when would I use that equation? This is the equation to use when two objects are at a different temperature. You put them together, and they will eventually reach the same final temperature. Right? And that's a thermal equilibrium problem. Okay, so if I pour hot water into cold water, they will mix and reach the same temperature, and you can use this. This is the temperature, might be the temperature lost by the hot water, has to be exactly equal to the energy gained by the cold water to reach that same final temperature. Doing it with water, hot water into cold water, here's a good hint. That's a nice thing to do on a multiple choice test because specific heat cancels out and all that. So you might want to look into that as a possible final exam problem. No, now you have to listen to the video. Just hot water into cold water. All right. This right here has to do with heat engines. If heat flows out, well, in order to get like a steam engine to work, a choo-choo train, right? They throw a bunch of coal or wood, or now it's diesel, and they boil water, and when that boiling water flashes steam, that steam pushes on a piston and so on. So you need a source of very high temperature, and that heat is going to flow out of the high temperature. You can turn some of that heat into mechanical work. The rest gets dumped into the low temperature environment. This is how your car works if you have an internal combustion car. It explodes gasoline. Gasoline is very hot when it burns. And so that heat will flow from that high temperature to the low temperature environment, and all those pistons and crankshafts and differentials, all of that stuff is just to extract some of that flowing heat and turn it into useful work. The rest of it goes right out your tailpipe. Most of it. Also, your engine gets hot and just radiates that heat into the environment. But in any case, the amount of energy lost from the high temperature source must exactly be equal to the energy dumped into the environment plus the energy that gets converted into work. Because what is always true about energy in any closed process? Energy is always conserved. If you have a closed system, that means there's no objects coming in and out. You're not adding mass. You're not applying any net force to it. It's all like one separate thing. Energy is always conserved overall. Maybe not mechanical energy is not always conserved, but energy itself in all its forms is always conserved. It's a law of nature. Okay, so if you understand all that and can use these equations and understand these quantities and understand the concepts involved in all this, you know enough to do well on the final exam for that unit. All right, now, this is the stuff we've been studying lately on electricity. But wait, there's more. I would say this stuff is going to be probably half, maybe 2/3 of the final. And then the other half to a third is going to be this stuff. I haven't written this stuff yet. I'm still working on the final. So, of course, you need Coulomb's law. And you need to understand the concept of charge. And that we have two kinds of charge. We have particles that repel like particles, and they attract the opposite particles. So we call that the capacity to do that. We call that charge. Protons carry the positive charge. Electrons carry the negative charge. And so we have Coulomb's law that describes how much force of attraction or repulsion we get based on how much charge we have. And we're going to assume that these are point charges. I'm going to give you 2 point charges, and I'm going to ask you questions about, like, are they attractive or repulsive? Do they, how much force is there? What's the electric field a certain distance away from things? And, I'll draw a picture for you, and you have to answer a bunch of questions about it. So charge, sometimes we use lowercase q, sometimes we use uppercase q for charge. Usually lowercase. Charge is measured in coulombs, and a big coulomb is a lot of charge. This is the electric constant, and it basically tells us, hey, electric force is very, very strong. If I've got a coulomb of charge and another coulomb of charge, and I put them 1 meter apart, there's going to be 9 billion newtons of repulsive force. 9 billion newtons. That's a lot. You wouldn't want to be anywhere near them. It's a lot of force. Compare that to gravity. If I put 1 kilogram a meter away from another kilogram, I would have 66 trillionths of a Newton. Trillionths. In other words, you'd barely feel it. This would drill a hole through you. I mean, if you're near that, and if you had an object, well, they probably vaporize in the atmosphere as they push each other apart. But you wouldn't want to be near it. It'd be an explosion. Okay, then we have the definition of electric field, and that's E with a vector hat on it. That's the electric field, and it's defined to be the force, the electric force, divided by the charge that's in that field. That's on the object that's in that field that you're measuring the force on. We call that quite often the test charge. And of course I've got, the quantities here. Electric field, E with a vector hat. What units? Newtons per Coulomb. And this little equation right here is when you take Coulomb's law and you divide it by, you use one of the charges as your test charge. And if I divided this by Q2, for example, it would tell me the electric field due to the charge Q1, a certain distance away from Q1. So if I ask you to find the electric field due to a point charge, you could use this equation here. If I have a charge that's in an electric field, and I move that charge in the electric field through a certain distance, or displacement really, I get what we call a voltage. I have a potential difference. That's potential energy per unit charge. It's the amount of work per unit charge I have to do to push an electric field, or push a charged particle in an electric field. Or it's, yeah. And we call potential difference, we also call it voltage, measured in volts. And it's the amount of energy you've got per unit charge. The amount of work you did, or the amount of energy stored up in your electric field because of the position of a charged particle in that electric field per that charge. Joules per Coulomb. Now, the other day when I was giving you the review outline, I did leave capacitance out, and that was an accident. So I'm adding it back in here. Capacitance, we use letter C for it, and it's really defined to be how much charge collects on a metal plate due to the voltage that I put across that plate. Okay, so if I have, I'll just draw it on here. You shouldn't put this on your equation list. Just if I hook this up to a battery, that battery is going to push positive charges onto this. Now, the more voltage the battery has, the more it can crowd these. It has enough energy per unit charge to force those charges together more closely. That increases the electric field across the plates. You get a very strong electric field, and then you always have the same amount of negative charge on this side. But the capacitance of this capacitor is just defined to be how much charge I get on the positive plate per volt that I put across, using this battery or whatever your voltage source is. And capacitance is measured in farads. We use capital F for farad, and it's coulombs per volt. Now, if I have a circuit where I have a closed circuit and I've got current flowing through it, I'm going to be putting energy into the circuit at a certain rate. That's the current times the voltage, and will equal power. And I have to define what current is. Current is the charge that goes by per unit time, or coulombs per second. A coulomb per second is called an amp. And then finally I have Ohm's law. And Ohm's law tells me how much voltage do I need to push an amp of current through some material, some object. And if an object has 20,000 ohms of resistance, that's a pretty high resistance, that means I need 20,000 volts, and then I'll get an amp of current to flow through it. If something only has like 3 ohms, or 0.5 ohms is a pretty low resistance, that means I only need 0.5 ohms means I only need half a volt of potential difference, half a volt on my battery, and I'll get 1 amp of current to flow through it. Like a bare wire. You know, take a battery and connect the positive to the negative side with a bare battery. That might be a resistance of like 0.01 volts per amp. And what's going to happen, you're going to drain that battery. The battery has its own resistance, so it's not going to be a huge current as much as you might think. But that's what resistance is, though. It's how many volts I need to get an amp of current to flow. And and here are the equations to describe it. All right. So here you go. Here's the equation list and quantity chart for electricity and magnetism. And here it is for the rest of the semester. I don't think I can get both of these on here. I can try. Oh, wait, maybe I can. Let's see. All right, you guys have a good lunch. There you go. That is all.